In the previous class, I told you in physics, we are not interested in identifying a real number is or whether it is a rational number or irrational number. There are two reasons. First of all, there is no reason why we increase the accuracy of measurement to infinitesimally small error. We hope to find the exact value. However, unfortunately, it is impossible. So from from Monday on, you will be able to download the PDF file, so it won't be a problem. Okay? It is impossible to increase the accuracy. In mathematics, you can claim this point is 0 and this point is 1. How? However, this line has its own thickness. If I increase the accuracy, the thickness of this line will be 0. I cannot draw anything. You cannot see anything. Something like that. So there is a physical limitation of measurement. So we cannot increase the accuracy of a measurement arbitrarily small. The best known physically measured values has 8-digit accuracy. That is still small, however, it has its own size. So any physical measurement has its own uncertainty. That is called errors. It's not wrong, it is just a real value is somewhere around a certain point with a certain uncertainty or errors. In addition, we can increase the theoretical accuracy by increasing the number of digits in floating point expression. For example, you learned sine x. Sure, you can make use on electronic calculator to find the value of a sine, whatever value of x it may have. However, there is a very nice way to approximate this value that is called Taylor series expansion, and so on. This one is not an algebraic function at all. It is a nonlinear function. However, we can expand this complicated function in terms of polynomials. You know, polynomials, powers of n, and n is an integer. These are all consisting of a very simple operation called addition, subtraction, multiplication, and division. So we can still be able to make use of a very, very elementary algebra to reproduce with a certain uncertainty that is called errors. And if you wish, we can decrease the theoretical errors arbitrarily small value. So this is a very simple example to show how to compute square root 2 that is also a nonlinear function with a purely algebraic method. Actually, square root 2 is the solution of this quadratic equation. And any middle school student can solve this equation, and they can write the solution of this equation is either plus square root 2 or minus square root 2. That is based on a very simple way to factorize this expression into this. And we know any product of number equals 0 if and only if only a single or both of them are 0. Therefore, if it is a 0, then we have a minus a square root of 2. If it is a 0, then we have a plus a square root of 2. Because we are interested in the positive solution only at this moment, we can choose this square root of 2. However, what is where this square root of 2 is? A simple way to find the position is draw a rectangle that has a square. This side, both sides are 1, and you will find that you draw a circle to find the place where it is. Okay, so you pin down a point where the square root of 2 is, and you bring a ruler and read the number. However, you do not have a very accurate ruler at all. At most, you can measure it 1 millimeter, something like that. So in order to increase the accuracy arbitrarily small, you need to do something else. So this is a simple way. It's very similar to the Taylor series expansion. This is just a simple warm-up. So let me go back to middle school, and we are very familiar with the expansion formula. Any middle school students second year, perhaps, they learn how to expand this. You are still familiar with this expansion formula. Now I claim this square root of 2 has the exact value a, but I don't know what the exact value is. However, I can guess some approximate value that is very close to square root of 2, so that x is an approximate value and the y is an error of my estimate. You know, 1 square is still 1. 2 square is 4. It's growing up and is a constant. What happens if I square 0.1? It's a 0.01. So it becomes smaller and smaller. This is a very nice idea. First I guess this error smaller than 1 and apply this expansion formula, then I can find that y squared decreases in comparison with our value previously obtained. This error is smaller. This is my trick. By making use of only algebra without calculator, I can compute this square root of 2 very accurately. Let's see. We try to make y approach 0, our uncertainty error. First, a is the square root of 2. I don't know what it is. However, I know 14 squared is 196. That is very close to 200. If I divide this number by 100, I know this is exact 2. Okay, so square of this, what's that? 14 minus over 10. 14 over 10 squared is 196 over 100. That is 1.96. That is very close to 2. However, it is not exactly the same as 2. This is my first guess of this approximate value x. And then we repeat this calculation to decrease the uncertainty, and at some point, the step n, I have obtained an approximate value for square root of 2 that is called x of n. And then I'm not able to compute the exact value of error. As soon as I obtain the exact value of this error, then I don't have to go further. However, it is impossible to find the exact value abiding by algebra only. So I can guess approximate value for the error and neglect the value coming from the square of this error. In this manner, I can improve my guess for the real value of square root of 2 by adding the next step uncertainty. And we must find my uncertainty error decreases step by step. If it is less than 1 indeed, then I can eventually find a very, very accurate number of square root of 2. This is my algorithm as a middle school student. Carry out the numerical computation of square root of 2 by applying this algorithm listed above. Let's do it. As the first step, I told you 14 squared equals 196 divided by 10 squared is 1.96, very close to 2, but less than 2. Therefore, we have this formula. I can cancel factor of 2 to find that 7/5 squared is square root of 2 squared less than, slightly less than 2. Okay, that's fine. Because this a is between these two numbers, we can guess that square root of 2, this is a, and our guess, a at exact value subtracted by my guess is 7/5. That is my error. And even though I do not know the exact value for the error, I know this is very similar to this. And this is very small. It is much smaller than 1. I'm fine with this because what I want to do is to make use of this expansion formula, but because this is very tiny, squared value is much more tiny. Therefore, in order to avoid solving quadratic equation, instead a linear equation, I remove this guy. If I remove this, my answer won't be an exact value. However, because this error is very tiny, my new value for this uncertainty is now obtained by solving this linear equation. I put bar in here because this y1 bar is not exactly the same as y1. That is an exact value, but this is an approximate value. Solving this linear equation, I can find it. It is a 1/70th. Now, my uncertainty of my guess has been decreased in comparison with a previous step's error. In such a manner, we can decrease this uncertainty arbitrarily small. Let's see if it is indeed So as a next guess, I use a previous guess, and now I have improved uncertainty. By adding this, I have a new guess for the square root of 2. We repeat this calculation as we wish. Okay, let's see. This one is just a copy, and then this is, why don't we replace this 1 by n? This is 2 by n plus 1. Use this method again and remove the higher order contribution that is believed to be much smaller than yn. Again, I obtain this. So because this y1 bar approximate value for my uncertainty is much smaller than 1, I can also neglect this. Finally, next step, I will have the same kind of formula. By the way, I know what these values are. Why? Due to this. And yn bar is determined in terms of previous guess, that is xn. So if I substitute this value in here, here, and then I substitute this value in terms of xn, it is completely expressed in terms of a previous xn. Let's see. This shows an improvement. It's a little bit tedious, but I don't want you to carry out this all difficult. It is not difficult. It is just tedious. Why don't we take the ratio of the next step error relative to the previous step error? Just copy these results in here. I obtain this. Be patient. Just simplification is possible. It's not a magic. And we know how to factorize. And denominator is in this form. We can now, this is just estimate. It is not exact value. We are not interested in finding the exact value using this error estimation. However, our goal is sum of this is a square root of 2. So even though it is not exact, they must be very close. Their sum must be very close to square root of 2. Therefore, square root of 2 subtracted by x of n should be y of n. And we don't know, there is no way to find a yn exact value. Instead, I can always guess the value of, approximate value of y of n. So that is my limitation. Okay, that's fine. And my value of x of n is not exact. However, it is very close to square root of 2. Therefore, in this error estimation, I don't make any big mistake in this just a rough estimate that I replace xn squared is just 2. This simple substitution leads to this relation. So ratio is proportional to the previous step error. It is very, very nice. Why don't we multiply y of n bar, both the sides? What we find is the next step error is the square of a previous step error divided by 2 square root of 2. This is a very, very tiny number. It is a remarkably efficient method to compute square root of 2. This is what I obtained by making use of this one, x1, x2, increasing accuracy, and this uncertainty becomes exponentially decreasing. Wow. This is actual error of my calculation. Have you ever seen the number of square root of 2 with 1,176 digits? I was really able to find this value using this. What about this? This is a 1176 digits value of square root of 2. Even though sine of x looks very, very complicated, however, in principle, middle school students can compute the square root of 2 just by using simple algebraic method if they are familiar with the kind of computer. Sure, the usual commercial computer program is not able to carry out the exact computation keeping this more than 1,000 digits. So be careful. And it is also impossible to produce these kind of numbers from palm-top calculator. Anyway, what physicists do, I don't really compute this 1,000 digits, but this is a very simple demonstration that even algebra is very, very powerful, and the derivation of, for example, the Taylor series expansion is not much different from this algebraic way of approximation. So you should be very familiar with this kind of developing algorithms for your future work. That's it for today.